So thank you for the introduction and thank you for the invitation to give this talk. It's a pleasure to participate on this workshop. So yeah, so my talk is about traversable wormholes in the context of ADS-CFT correspondence. So this talk is based on some of my recent work on this topic. And the work was done in collaboration with Byung-Jung An, Young-Jung An, Sung-Gun Bak, and Kyung Kim in Korea. Okay, so yeah, so recently Gao, Jeffries, and Wall realized that wormholes in ADS can be made traversable by coupling the two asymptotic boundaries. And from the perspective of the boundary theory, the traversability of wormholes in ADS can be thought of as a teleportation protocol. So most of the works about traversable wormholes were done in lower dimensional systems. And as far as I know, the effects of conservation laws on traversable wormholes have not been explored yet. So in this work, we study D+1 dimensional wormholes that are made traversable by coupling the two asymptotic boundaries with conserved current operators. So let me give you some motivation for this. Yes, so the traversability of wormholes is deeply connected to their scrambling properties. And on the other side, the scrambling properties of black holes change under the presence of conservation laws. For instance, OTOCs involving conserved current operators display a power law behavior with time, which is different from the typical exponential behavior that one observes in when the OTOC involves scalar operators. So this suggests that conservation laws affect the traversability of wormholes. For example, the wormhole opening can, in principle, depend on the transport properties of the horizon. And I think this might have important consequences in many-body quantum teleportation protocols. Yeah, so the type of setup that we are going to consider is shown here. So we are going to be considering two-sided asymptotically ADS black holes. So the boundary will live in flat space, and we are going to considering a metric of this form. And when we consider a two-sided black hole of this type, we know that this is dual to a thermal field double state, which you construct by entangling the two boundary theories. So we have a CFT here that lives on the left boundary. You have a CFT that lives on the right boundary. And when we consider a thermal field double state, this corresponds to the holographic dual of this two-sided black hole. And if we consider, for instance, a constant time slice here, this has the profile of this constant time slice has this wormhole type of geometry. Okay, so we are going to consider this type of geometry, and this wormhole here connecting the two asymptotic regions is not traversable. And the non-traversability of this wormhole is related to the so-called average no energy condition, which I now will try to explain. So basically, the average no energy condition states that the integral of the stress energy tensor along null geodesics is positive. So that basically tells you that the energy of your matter fields should be positive, and that prevents wormholes from being traversable. Let me try to explain why this happens. For instance, let's say I want to send a signal from the left region to the right region. If I send the signal from the causal structure here, I see that the signal just hits the field.
Maybe I ask a question. Maybe I am wrong, but as I remember with Morris Thorne conditions is true for flat, asymptotically flat case. And in this case, you deal with ADS.
Yeah. So I think you're right. Like there is a proof about this asymptotic flat space, but I think there is also a work about the ADS space, but I don't remember the reference now. I'm sorry about that.
Okay, thank you.
But so basically you just, the signal just hits the future singularity and never makes it to the right boundary. So you say, okay, maybe if my signal interacts with some matter fields here in the horizon, maybe the signal will be able to cross to the other side of the geometry. So you can imagine a situation where you include some matter fields, which are shown here in red, and you try to understand whether these matter fields will change the picture and make the wormhole traversable. And it turns out that this matter field will have some back reaction on the geometry. Here I consider a situation where the matter field have a very simple back reaction in terms of shockwave geometry. And this shockwave type of geometry changes the trajectory of the signal in a very simple way. It just shifts the trajectory in one of the node directions. And if you compute this, you can see here that the shift is basically proportional to the integral of HVV dV. So however, if you use the equations of motion, you can see that this integral of HVV is actually proportional to the integral of the stress energy tensor. And we know from average no energy condition that this integral should be positive. And so basically that implies that the shift in the trajectory is also positive. So the interaction with the matter field only makes the situation worse because your signal still hits the future singularity. So another interpretation of this is that this matter field has some positive energy. So it basically, when this falls into the black hole, the horizon increases a little bit. Let's say the wormhole becomes slightly bigger. And that makes a little bit more difficult for the signal to escape from the black hole. So and this condition, like if you consider a classical theory, you actually, in general, like for classical theories, we have, they respect no energy condition, which basically says that the integrand here is positive. So classically, it's impossible to construct a traversable wormholes unless you have like some exotic matter with negative energy. So to construct a traversable wormhole, Gao, Jeffries, and Wall consider quantum mechanical effects. So let me briefly explain their construction. So they work in the context of the semi-classical approximations. So just as in the case of one stock, they consider like the gravity field is treated classically, but the quantum mechanical, the matter fields are treated quantum mechanically. So they basically introduce a coupling between the two asymptotic boundaries, and by choosing the sign of this coupling, they can introduce some negative energy in the bulk, and this makes the wormhole traversable. So I will try to explain this with some more level of details, and how is it possible to have some negative energy in the bulk and so on. So the first thing to say is that this, even though it's weird to talk about negative energy, this is somewhat similar to the Casimir effect. So in the Casimir effect, you have two conducting plates, and you compute, for example, the vacuum energy between the plates and in the region outside the plates, and you realize that the result you get is actually infinite. But if you subtract the energy inside from the energy outside, you get a negative result. So basically, what this is telling you is that the boundary conditions that your electric field respect here inside the plates reduce the energy a little bit below the vacuum energy. So if you define the vacuum energy outside as 0, then the energy inside will be negative. So this is somewhat similar to what happens here. So when you have a coupling of this type, you're changing the boundary condition for a scalar field in the bulk, and this creates a quantum correction to the to the stress energy tensor, and this quantum correction is negative. The full energy, the total energy is actually positive, but this quantum correction is negative. Okay, so that's my explanation about the negative energy. So yeah, from the boundary perspective, this is actually very interesting because yeah, so basically you introduce some matter, so you act with some operator on the left side, and you introduce some matter fields on the left side of the geometry. And as you probably know, the fact this bulk field excitation falls into the black hole, and from the boundary perspective, this has the interpretation of a thermalization of this excitation. So if you think about this process from the point of view of the boundary, what's happening is that, let's say the two boundary theories live on these planes. So you excite one of the boundary theories, create some perturbation. This perturbation thermalizes, completely disappears in the thermal bath. And then you introduce a coupling between the two theories. And after some time, the perturbation rematerializes on the other system. So from the point of view of the boundary theory, this is kind of amazing. And that's the picture. And that actually has the interpretation in terms of a teleportation protocol, but it's actually a new type of teleportation protocol, because here you have actually many body quantum systems, as opposed to the more conventional teleportation protocols, which involve just a few qubits. So for example, in a conventional teleportation protocol, Alice has a qubit that she wants to teleport to Bob. And what she does, and they both share a EPR pair. So Alice basically performs a Bell measurement in her qubit, in her two qubits. Then there is she communicates the process to Bob, and Bob applies some unitary operation and recovers the qubit. So here it's almost like conceptually, it's like you're replacing the EPR pair by a thermal field double state. So the time evolution operator it's more complicated. It's a many body time evolution operator, but conceptually is the same thing. But the idea here, what's kind of surprising here is that the information initially gets scrambled with the other degrees of freedom of this system. And then after this classical communication, which represents the coupling between the two systems, the information reappears on the right side of the geometry. So yeah, so this type of experiment, this is a new type of teleportation that some people call this many body quantum teleportation. And I think the experimental realization of this type of quantum teleportation in systems that admit some sort of emergent gravitational description might give us some clues about the inner working mechanisms of gauge gravity duality. And this type of teleportation, many body quantum teleportation, was recently simulated in Google's quantum computer, Sycamore. Okay, so yeah, so let me mention a few things about the Gauss-Jeffreys-Moll result. So they consider deformation that they apply the coupling between the two sides, and the coupling remains in the system forever. So the deformation that they consider is like a theta function type of deformation. And they find some result for the average no energy, which depends on delta, which is the scaling dimension of the scalar operators that they are using to open the wormhole. And it also depends on V0 here, which is related to the insertion time, the time at which they included the deformation. So their formula is somewhat complicated, but if you consider a delta type of deformation, you can obtain a much simpler formula, which is shown here below. And from this formula, you can actually see that at late times, the average no energy decays exponentially with the insertion time. And I'm going to use that just to compare with the results that we observe when we open the wormhole with conserved current operators. Yeah, so before talking about conserved current operators, I would like to briefly mention possible generalization of Gauss-Jefferson-Wall teleportation protocol to higher dimensions. So this formula here can be generalized to higher dimensions. And the way to do that is to consider, for example, the framework of Ringler ADS CFT. So you start with global ADS, and you consider basically the Ringler coordinates in global ADS. So Ringler coordinates only cover some region in global ADS. And if you consider the maximally extended version of this geometry, you end up with some sort of two-sided black hole where the boundary CFTs live on hyperbolic space. This is actually like a topological black hole. It's just like pure ADS in these guys, but this type of setup can be used to study Gauss-Jefferson-Wall protocol in higher dimensions. And I did that some time ago, and we were able to basically generalize Gauss-Jefferson-Wall formula for a higher dimensional setup. So that we have this complicated formula. And if we consider d equals 2 here, we recover Gauss-Jefferson-Wall result. And what we can see here, for instance, in black here, we have Gauss-Jefferson-Wall result. And as you increase the dimensionality of space-time, you can still have a violation of the average no energy condition, which makes the wormhole traversable. But this violation decreases, like the absolute value decreases as you increase the dimensionality of space-time. So these plots are for fixed H, the coupling. We fixed the coupling between the two boundaries and increase the dimensionality of space-time. In higher dimensions, it's also possible to consider a two-point function that diagnoses traversability. And considering this two-point function, we can actually find some sweet spot for traversability. For a BTZ black hole, some people observe that this sweet spot for traversability is controlled by some light cone. And here, in higher dimensions, we observe that this is controlled by a butterfly cone. So basically, if you fix the position at which you want to observe your signal, you can find some region in time which defines this sweet spot for traversability. I can give you more details about this work, but this is just like just to comment on a possible generalization of Gauss-Jefferson-Wall protocol. Now I would like to sort of try to explain in detail Gauss-Jefferson-Wall calculation, but instead of considering scalar fields as they considered, I would like to consider conserved current operators. So basically, we are going to consider a coupling involving, for simplicity, we couple the two boundaries with just with the time component of a conserved current operator. And the basic idea here is that this coupling will introduce some negative energy in the bulk and make the wormhole traversable. So let me try to walk you through this calculation now. So the basic idea here, so basically, so one thing, like we are acting with some boundary conserved current operator on the boundary CFT, and this introduces some bulk field. This is due to some bulk field, which is I'm writing here a gauge field. So yeah, so I'm going to consider the equation of motion for this bulk field. So the gauge field stress tensor, it has this form, and I'm going to consider a general background of this form. So we are interested in computing the VV component of the stress energy tensor. So for simplicity, we are going to set the spatial components to 0. And once we do that, we find that the stress energy tensor at the classical level is basically given by a dot product of the gradient of the AV component of the gauge field. So here, to compute this, to consider this at the quantum level, we use point splitting to compute the quantum expectation value of this stress energy tensor. And the idea here is to separate, to compute each field in one point, and then we take the limit x going to x prime in the end of our calculations. So the basic idea here is that the stress energy tensor can be obtained from the properly regularized bulk two-point function. Fortunately for us, like the zero order contribution for this two-point function really diverges, but the zero order contribution doesn't open the wormhole. And the first quantum correction is actually finite. So let me give you some more details about this. So we want to compute this bulk two-point function under the presence of a perturbation like this. So basically, we use perturbation theory and compute this at first order in perturbation theory. So as I told you before, we are going to have like G0, which is the zero order contribution, and this actually diverges. This diverges, but it doesn't open the wormhole. And the first quantum correction, which is proportional to H, it's actually finite. And this can be leads to a non-zero value of the average no energy. And by choosing this H, this coupling, we can find a situation where ANEC is actually violated. Yeah, so if you plug this deformation into the above formula, you'll find some formula for this two-point function, which basically depends on bulk boundary propagators involving the gauge field and the boundary current. And this is sort of complicated and cannot be obtained in general, but we can compute these propagators using a hydrodynamic approximation. So unfortunately, we cannot do this calculation in the general case. We have to rely on this hydrodynamic limit. And we actually observe that all the propagators that we need to do this calculation can be obtained from a bulk propagator GTT, which is basically a bulk propagator involving the T component of the gauge field. So basically we consider ADS Schwarzschild black hole with metric of this type, and we solve the equation for the gauge field in the bulk. And by solving this equation in momentum space, we actually find this typical diffusive behavior. And this diffusive behavior is controlled by a charge diffusion constant. And it leads to, if you go to position space, you find a behavior like the one shown here in the picture. Okay, so this is just like, I'm just showing you how this charge diffusion constant pretty much controls the behavior of the gauge field. And the gauge field will be the guy introducing negative energy in the bulk. So actually what we have to solve in the bulk, it's actually we need to find the bulk propagators. So we need to solve these equations with the source. And this can be done. And the behavior of the retarder propagator, for example, is also controlled by this charge diffusion constant. And we can obtain the retarder propagator, the Weintraub propagator, and those are ingredients that are necessary to compute the stress energy tensor. And once you compute the stress energy tensor, we can compute the average no energy condition and find our our result for the diagnosis, the traversability of the wormhole. Yeah, so by doing this calculation for an instantaneous perturbation, we find the following result. So basically, V0 here is related to the insertion time. So basically, we observe the same exponential type of behavior that has been observed before for scalar fields, but there's also some sort of power law behavior that is reminiscent of the power law behavior that one observes for two-point functions in the hydrodynamic limit. But the most interesting thing about our result is the fact that the average no energy actually is proportional to the charge diffusion constant. And it's inversely proportional, actually. So in general, this sort of suggests that diffusion makes it harder to open the wormhole. However, on the other hand, it seems that the average low energy condition also becomes arbitrarily large if you set the charge diffusion constant to, if you set the charge diffusion constant to 0, for example. So we have this interesting dependence, and yeah, so for our, so we did this calculation for short shoot ADS, but we believe this result is actually universal. So we are currently trying to show this universality, this universal behavior, and by doing that for like a general metric. And anyways, like, so if you have a system, for example, in which this diffusion constant is controlled, for example, by an external parameter, you could like change this external parameter and maybe make this diffusion constant, for example, very small. And if you make it very small, the wormhole opening would be very big, for example. And this could, for example, favor traversability. So yeah. So by the way, I think this type of, so we consider U1 gauge field operators, but not gauge field, sorry, U1 current operators, but this should be true, I guess, for other types of conserved currents as well. So let's move on. So basically the physical picture here is that the diffusive behavior of this gauge field gives rise to a bulk field excitation, which sort of like diffuses in the bulk. So when you send a signal from the left to the right boundary, this signal needs to interact with the negative energy to be able to cross to the other side of the geometry. However, in the case of the gauge field, this negative energy diffuses, so the collision takes place in a region that is very huge. So the collision is kind of mirrored in a large region of space-time points. And this is, in general, this makes the collision like weaker. So it becomes, in general, more difficult to cross to the other side of the geometry. But on the other hand, we have this interesting dependence on the charge diffusion constant. Okay, so, oh, sure.
So this you have this dependence on diffusion because your coupling involves the time component of the charge density.
That's true.
If you coupled with the space component, presumably it doesn't have a diffusive pole, so this wouldn't happen, right?
Yeah, that's true. That's one motivation to consider the time component. It was because it displays diffusion. For instance, we could have done this, for example, in the framework of Ringler ADS CFT, because in this framework, we actually have the precise formula for the propagators, bulk boundary propagators. However, in this case, for example, the propagators are well known for PTZ geometry or Ringler ADS, but in this case, we have no diffusion. So I don't think that, I mean, like the calculation can be done, but then there would be no interplay between traversability and transport properties. So that was kind of our motivation to consider the time component.
All right, thank you.
Yeah, sure. Thank you for your question. Yeah, so basically, so this picture kind of suggests that in general, it's not a good idea to open the wormhole with conserved currents, because it's kind of more difficult to have a successful teleportation. But on the other hand, if we could control the diffusion constant by choosing some specific geometry where we can tune the value of this diffusion constant, maybe we can find a situation where traversability is kind of favored. But anyways, like I would like to mention a few things about the bound on information transfer. So yeah, so you can send a signal from the left to the right, but if you try to, so let me explain this more carefully. So a traversable wormhole allows you to send a signal from one asymptotic boundary to the other. However, the back reaction of the signal tends to decrease the wormhole opening. So as a consequence, if one tries to send a signal containing too many particles through the wormhole, the back reaction of the signal closes the wormhole. So that, together with the uncertainty principle, implies a bound on the amount of information that can be transferred through the wormhole. And so let me try to explain this with some more detail. So consider a signal with any bits, for example, any particles. Any bits is just like, I'm just counting the number of particles. And each particle with momentum p each. So the total momentum of the signal will be number of particles times the momentum of each particle. So you can say, okay, if I send many particles with very low momentum, maybe I can send as much information as I want, right? However, if the particle has very low momentum, then the wave function is kind of occupies a very large region in space, and this wave function does not fit the wormhole opening. So by the uncertainty principle, one can basically find that the momentum of each particle implies that the corresponding wave function occupies some space, which is denoted as delta U each here. So basically, if I want the wave function to fit in the wormhole, I need to impose that this delta U each should be smaller than the wormhole opening. So then if I play a little bit with these conditions, I can find that the number of bits that I can send through the wormhole should be smaller than the total momentum of the signal times the wormhole opening. Now, if I want to keep things in the probe approximation, I need this additional condition. And by using this sort of reasoning, Maldacena, Stanford, and Young were able to derive a bound on the amount of information you can send through the wormhole. So if you consider this formula with Gauss-Jeffreys wall construction result, you can see that the number of bits you send through the wormhole is basically smaller than the h, which is the coupling between the two sides. So here in our construction, we find that the number of bits also depends on h, but we have a temperature dependence here, and also a dependence on the dimensionless charge diffusion constant here. So basically, our result sort of suggests that, for example, if the charge diffusion constant is very big, then it's harder to cross the wormhole, which is kind of easy to see from the physical picture that I showed you before. But if I have a system for which d can be made very slow, then maybe I can send this bound can be the right-hand side can be bigger. And also another consistency check here is that if I plug the temperature to 0, if I set the temperature to 0, meaning there is no black hole, then the right-hand side is 0, and I cannot send information to the other side. So yeah, so we have this interesting dependence, and currently I'm trying to show that this happens like in general for any type of geometry, as long as you have a gauge field with this diffusive behavior. I think this should happen. Yeah, so yeah, my conclusions is that it's possible to generalize Gauss-Jeffreys wall traversable wormhole construction to the case where the double trace deformation involves U1 conserved current operators. But I think this is in general for other conserved currents as well. For instance, if you use, for example, the stress energy tensor to open the wormhole, maybe you find not the charge diffusion constant, but for instance, the shear viscosity, for example. In our case, like the wormhole opening depends on the charge diffusion constant and is inversely proportional to it. And I think a similar story should also be true for other conserved currents. So as a future directions, I think it's interesting to consider other types of conserved currents and fields, and also understand how bounds on diffusion constants affect the bound on information transfer. For instance, sometimes I think like, yeah, so basically sometimes these diffusion constants have a upper or lower bound, and this might have some importance on the bound on the number of bits you can send through the wormhole. And I think it's also interesting to study that from the point of view of the boundary theory in the context of the many-body quantum teleportation protocols. So yeah, I guess I was too quick. But that's pretty much all I have to say. So thank you very much for your attention.
Okay, thank you very much for your very interesting talk. Questions, please. Please raise a hand or just ask questions. In fact, we had some questions during the talk.
Sorry, I have a question.
Okay, please.
Oh, yes.
Yeah, what you did is, okay, introduce these gauge fields and they give you a diffusive propagator. What would happen if you would consider the hydrodynamics of the wormhole itself? So just consider a metric perturbation. Would that differ significantly from what we know for black holes? Or you expect
you mean like you don't think about you want to use only the metric field to open the wormhole?
No, actually, when you have already opened it, so what would happen if you would consider metric perturbation on top of it? So like repeat the classic calculation of hydrodynamics, but just so not for a black hole, but for a wormhole. Would that give something interesting or?
Oh, that's an interesting question. I have not yet analyzed that, but you mean like you consider the corrected version of the metric, like
yes, yeah.
and then consider fluctuations around it.
Yeah.
I think that's an interesting question. I have not done that, but I think that's an interesting future direction. What do you have in mind when you consider these fluctuations?
Well, just, I mean, I'm wondering whether it would differ significantly from what we know for black holes, or it would just be a perturbative correction. I mean, would you find a significantly different hydrodynamics because you have now this teleportation or?
Okay, I see.
Just wondering what's hydrodynamics like in a system with teleportation, so where you have also this non-local transfer.
Yeah, I mean, like that's a very interesting question. Yeah. Because you do have a non-local coupling, so maybe something funny will happen.
Yeah. Thanks.
Okay, more questions?